Okay, so I'm going to take the next hour to try to share with you as much as I can the new syntax related to the draft document we have today for generics. A couple of things before I start. One, you need to understand that generics has not been implemented yet in the language at all. What you're looking at, or what we're going to be looking at, is a proposed syntax and a transpiling tool that will allow us to play with this new syntax. So it has not been implemented yet at all. But that being said, the first step is for the larger community to come together and agree on the syntax, because once this does get in, let's say a year and a half from now, I mean, there's no going back. So we've got to solve this problem first. And that first link that I shared with you is to this repo in the training repo that I have. And within the scope of an hour, we're only going to really have time to get through the first, I'd say, about 5 examples here. But these 5 examples will give us the bulk, the 85–90% of what the draft is sharing today with syntax. So it will be good. And it's 40 minutes after the hour, so I'm going to watch that clock as we go. Now, that first link I gave you again, which is this repo with examples. A couple things here. There is a link here, and it's the second link that I provided you in the chat, which is going to be giving you access to the draft design. This is a living document. They're updating it as they need to. And this would give you the core kind of documentation. But I'm trying to save you from having to read this if you haven't read it already, and dig deep into code. Also, the team has published a playground that will allow you to also play with the new syntax. It's go, and it's just using the transpiling tool. Now, I'm not going to be using the playground here. I have not the latest, greatest, I think it may be a week old, the source code for Go, and I've checked out the branch for the tool, and I'll be running it locally. One of the things I did steal from the document, I'm not going to read this, is the high-level overview of what the draft is currently implementing in terms of generics and what we could consider probably being part of a first release. So nothing's written in stone yet. I've also taken from the document not just a high-level overview of what I'm going to try to show you as much as I can over the next hour, but the things that are currently not being considered for the first release. That doesn't mean that these things don't eventually make it into Go in releases after the first one, but right now these are not things that are being looked at or worked on. Got some extra reading, and then if you want to install the Go tooling locally, these are those instructions to do that. It's what I've done right now. And if I were to switch over to my terminal window, type Go version, you'll see I have a version of this from July 30th. So I'm not running like a 1.14 or 1.15 beta, or maybe even a release candidate. I'm not running that. I'm running here from dev there. So we see that, and that's how I'll be running the examples. Okay. All that being said, I want to jump into code since we don't really have a lot of time. An hour seems like a lot of time. It's going to go pretty fast. And again, the goal here is for me to try to show you the current syntax choices for generics, hopefully give you a sense of where this first release of generics fits in terms of the problems that it's going to try to solve. And give you a few opinions along the way. So please use that chat to talk among yourselves and debate things that I'm showing you. And then at the end, I'll grab your questions. I'll do my best to answer them. All right, so we're going to start here. And again, I'm going through that code that I shared with you in the repo. All right. So let's say right now, using the current version of Go, I wanted to write a print function that could print a collection of numbers from a slice of integers. So you see on line 13, I got my print numbers function. It accepts that slice of int. And then with 5 lines of code, I can print a label. I can use our traditional for range loop, range over, do that linear traversal across that slice of integers. And then just leveraging print right now, I can print each individual number. So 5 lines of code, you're seeing that. And I would argue that I think most developers at almost all different levels could understand and that code that that I'm presenting. I can understand it, can comprehend it, can read it. There's not much there, and it's why we love Go so much, because you can just come into the language even within a couple of weeks and kind of understand what you see there. Now, if I wanted to do the same thing with a collection of strings, well, because I'm changing the data type from an int to a string, I have to write a new function. And that's what you see on line 21, the print strings function. And it's essentially the same 5 lines of code that we saw. The only difference is I've changed the variable names and the type information. But there it is. If I wanted to print a slice of floats, here we are again. I got to write another function, takes the floats, rename some variables for readability, and there we go. But again, the code is 5 lines of code. Everyone can comprehend it, maintain it, and there's some value in that, right? So the next question that comes to mind then is, well, is there a way to do this with a single function? And when you think about it, you could eventually get to this solution. Now, this is a function that I called print assert because it's leveraging type assertions in the language. So you can see that this function is going to accept a slice of int or slice of string through the use of the empty interface. And the empty interface is a way of accepting data of any type because there isn't really any constraint on what the data is or what it can do. And through the use of the empty interface, I can accept that slice of int or string. I can perform a type assertion on line 37, then perform conditional logic on what type of slice it is. And if it's an int or a string, in this case, I can perform that linear traversal using my for range and print it out. Now, really, all I've done here is consolidated 2 functions into a single function. But I'm still limited by the number of case statements that I choose to code here, right? I've just consolidated the 2 functions into case statements. I wouldn't argue that this is a generic function because if I pass a slice of float into it, I'm not going to see anything. So then the question is, well, okay, this is good. I can accept any type of data I want, but I'm still bound to these type assertions, which means specific implementations. Is there a way in the current version of Go to write a print function that's fully generic? And the answer is, yeah, there is. And you can see here on line 56 that I'm still using the empty interface to accept a slice of any given type, but the code is getting a little bit more complex now because I'm going to use the reflect package. And we see that on line 58 where I call reflect.value of. On line 59, I can pair the data that was passed in to being a slice. And if it isn't a slice, I have to return something. So I'm kind of changing the semantics a little bit here. I'm not doing any error handling, not like the original functions did. But knowing that it's a slice, I can still do a linear traversal, even though it's not with my for range. I can make some method calls off of that reflect value, like get into the index of each element of that slice, use the interface method, and then I can print out whatever that is, whether it's an int, a string, and now even a float. So arguably, I do have a generic function here. I can pass in a slice of any type and display the individual values thanks to the use of the reflect package. I have written code that's a little bit more complex. I went from 5 lines of code to about 8, and most people, including myself, will have to look up the documentation for the reflect package to get a better understanding of what's happening here. So it's not as cut and dry as the other code. I can't make the same argument that Go developers of almost every level can come in and just intuitively comprehend the code that I've written. But there it is. I mean, it's a generic function. We can prove that. Now, I am gaining some benefit from the fact that the print function in the from package is also using reflection to display a value of any type. So we're kind of leveraging the fact that print is a generic function as well. Okay, so I'm making an argument that we have the ability to write generics already in Go through the use of the empty interface and reflect, but the complexity is greater because we're working with an API instead of actually working with pure Go syntax that we saw before when I was working directly with a concrete type. So the question is there value in being able to take the original code that we wrote, like here for the slice of string, but be able to write that code in a more generic way? And I think the answer is yes, in the fact that we should be able to leverage the same 5 lines of code that you see there and kind of replace the type information more than replacing and copying and pasting code and or leveraging a new sort of API around reflection. And this is one of the problems, the use of the empty interface and where we're using the empty interface and reflection today and or type assertions today, where the current draft could reduce some complexity, make code more readable. So on line 75, we're looking at our first sort of view of the generic new syntax in this form of a generic function. And what I really want to do is kind of break down why we even need any new syntax. So I'm going to remove this for a second. And what I'm going to do is kind of just talk about this function like this. Now, the first thing I want you to do is notice that the 5 lines of code here inside of our print generic function is really identical to that code that we started with our slice of int and string. We're back to those 5 lines of code. We're back to our for range loop, our linear traversal. We're back to using print the way we did it. And again, I want to make the argument that we all, Go developers just about at any level, can read and comprehend and understand that code. But the thing here is that what we want to tell the compiler is that we want this function to accept a slice of not really t, but of some type t to be determined at compile time. The point here is that we don't want to explicitly define what t is here. We want it to be determined at compile time. Now, it would be really great if we could just write this code like this, but the compiler is going to assume with the syntax that you're seeing in front of you that this t is a type that's going to be declared at some point in some file before we ask to build the program. So the compiler is going to assume that I do something similar to line 75, that we declare this type T before I hit build. And the reality is that this is the exact opposite of what we want. We don't want to pre-declare this type in some way. We want the type T to be determined at compile time in some way. And so we need some new syntax to allow the compiler to know that you shouldn't expect me to define T explicitly like type T struct, that we're going to determine what this is at compile time. So the current draft suggests that we use this syntax here to define a list of generic types to be determined at compile time. In other words, to be able to satisfy to the compiler that T does represent some type to be determined at compile time that we're not going to define explicitly ourselves. Now, we can see here the use of the square brackets in between the function name and the parameter list. And we can call this a type list, right? I call it a parameterized type list of generic types. Now, the draft also currently supports the use of the parentheses here. This is really, the draft started out with the use of parentheses to get us going. And up to a couple of weeks ago, we were now able to start using the square brackets. I feel pretty strongly that the square brackets are probably going to stick, and they do help with readability applying this new syntax. Now, a lot of people were initially calling for the use of the, say, traditional in C++ and Java angle brackets. The language is not supporting this, and honestly, it can't support it for backwards compatibility. So it's just not feasible. And if I have time at the end, I can show you through the use of a blog post that I wrote why it's just not feasible. But for now, if you're having that chatting conversation about wanting to use angle brackets, and because of the time I'm under at this point, it's not feasible. It's just not going to be an option. And the square brackets right now seem to be the leading contender for defining this type list. Okay, great. So we're seeing this generic function. We're seeing how we're writing code again as if T is some concrete type, and T will be a concrete type, just not defined by us, but to be defined at compile time. And you're seeing the new syntax to help us identify that T is this generic type. All right, let's run this code a little bit just so we can kind of see it. And what you see on line 86 is this construction of a slice of integers. On 92, you see the construction of a slice of strings. And ideally, I pass that same slice across all of these functions that we've written so far. And if I come into 01, we should be able to run some code. Now, I'm using that version of Go that I shared with you. And this version of Go does not have generics implemented yet, but it does provide a Go tooling, which is a transpiler. So I'm going to be able to give it a source code file with a Go2 extension, which has got our new syntax in it. And the Go tool will be able to transpile that into a regular Go file, and then we can build it and run it. I did forget to use the run command, so let's do that. And if I run that, you'll see that all of those functions that we've written are working with that slice of int and string. Now, the whole point here is that I should be able to do something like this with our generic functions, right? I should be able to maybe change that to a float 63 and apply some floating point numbers in there. Maybe we call this floats. And these are the only two generic functions that we really have. I can pass floats to reflect. I can pass floats to generic, and I don't have to write any code like I would if I was going to have a print floats or add another case to print assert. And so you can see here that I'm able to output those floating point numbers, both with our reflect and our generic functions. Okay, great. So we're seeing here this generic function. Now, one more aspect of this that's going to come up is that the compiler right now is capable of identifying what T is, or we can say inferring what type T is at compile time by looking at the slice that we're passing into the first argument, since this T is representative of the argument itself. So you can see that numbers and you go, okay, I know T is going to be an int here. I know T is going to be a float 64 and a string. But the syntax doesn't limit you, and in some cases you may need to do this to explicitly state, as on this function call, what T is going to be. So these brackets also serve as a way of not just defining a list of parameters, but being able to pass that information in as well here at the call site. So I can build and run this as well. Everything's good. And instead of asking the compiler to infer the type in this case, I'm telling the compiler what T is going to be at compile time. All right. But I mean, the reality is that if I have to do this with all these function calls, well, you know, we are making things a little bit more difficult for everyone to read and write. So the ability of the compiler to be able to infer, in this case, based on the data that we're passing in, infer what T is really, really a critical part of the draft and the implementation. Okay, so we've got all of that. Let's see, that's 20 minutes in. Okay, it's 2 o'clock. So I've shown you some of the base syntax now as relates to functions. Let me kind of shift gears just a little bit and share with you code where we can apply generics to some user-defined types, some named types. And let's go through a little bit of the same progression, because I think it really helps to kind of see where generics is fitting in and maybe help to see the complexity it can reduce in some of our code bases. So on line 11, I'm defining a user-defined type, a named type called vector int, and it's based on a slice of integers. Another way of saying that is that vector int has an underlying type, which is a slice of int. And if you look on line 18, the new type vector string has an underlying type of that slice of string. So these are two types. They're not struct types. They're types that are based on existing types, in this case, slices of both int and string. Now, just to add a little more fun, since these are vectors, on line 13 and 20, I add a push method. And you can see we're using our value semantic mutation mechanics, where push gets its own copy of the slice used to make the call. It mutates that slice, or it adds a new value based on the data being passed in this case it int, and then it returns a new version of the slice, or in this case, the vector. And we're using the built-in function append to perform the actual push operation. And if you look on line 20, we have really the same method. The only difference is it's bound to our vector string, and it works with strings and not ints. Sorry. And the code is incredibly similar, minus the fact that one's working with integers and strings. And I just want to make a point that the bulk of the work is happening in append, and that when you really think about all of the built-in functions here in Go, again, you start to realize that Go already has generics, doesn't it? I mean, It has it with the reflect package. We saw that with print. We saw that with func.print and the other function. But append is a built-in function that can work with any slice of any type, and given a value of the same type, and perform that operation. So Go really has generics already. The problem, though, is that when it comes to the built-in functions, the mechanics for writing generic functions in Go isn't extended to us. It's really limited to the language and the language team, right, to write these built-in functions. So I just want to make a point that Go really does have generics already, and we've been leveraging that quite a bit already for the last 10 years. The reflect package is extended to us, but the mechanics that go into append aren't. So we can make these arguments, but because it's not extended to us as easily, right? We could feel like it's really not there. But we've got our vector int, and we've got our vector string, we've got our push. Now, we go back to, well, can I do this in a more generic way today? And the answer is, yeah, you could. You could change that vector to be a slice of the empty interface. Again, because append is already a generic function, the implementation of push is really no different than what we saw with string or int. And again, a lot of that is coming from or thanks to the append function. But this vector does change semantics, because when you think about it, the other vectors were tied to one specific data, which really helps with usability because you know what you're getting in and out. It's either an int or a string or something specific. When it comes to this vector using the empty interface, well, the semantic change is that you're not tied to any given concrete type. I can interlace different data values in this vector. And though the implementation looks incredibly similar to, say, string, so there's no maybe extra complexity there, the usability of this vector is where the complexity kind of kicks in, and I'm going to show you that. But what would this look like as relates to being a generic type? And so if you see on line 46 here, what we're going to do is define this in a generic way. Now, once again, I'm going to get rid of that. And I find it's just easier for me to initially read the code without applying some of the new syntax. So the idea is that I'm trying to define a type named vector generic that's based on a slice of some type T to be determined at compile time. Again, it's some type T, not T itself, but to be determined. And so anytime we're back to this idea that we want T to be a type to be determined at compile time, then we need to apply this syntax to help tell the compiler, don't expect me to define T, not explicitly. Don't look for type T anywhere in any source code file. We're going to tell you about this at compile time without me having to declare a new type. So that's what those brackets again are there. Vector generic slice of some type T. Now, because a vector generic is bound to some type T, you can see this syntax being played out again in the receiver and the return, where the value being passed in is also a value of some type T. And then again, because append is already a generic function, it all works. But you're seeing now how we get to find this user-defined name concrete type that's going to be based on generics, in this case, an underlying type. Okay, so let's just run this code a little bit. So you can see here, I'm going to construct that vector int, set it to its 0 value. I'm going to push some integers through. I'm going to use a traditional for range loop. And because I know that this vector only works with integers, I could get very specific here and say %d is a format specifier, not have a single issue. Because again, I know that this vector only works with ints, there's no issues. Same thing with string. It's all the same code, so we're pushing strings in there. The push methods know to work with strings. And I can do a %s. I got no issues. Now, I told you the implementation of vector interface was pretty much on par with vector int and string, but the usability is where we're going to start losing, our readability. It's the usability that adds the complexity, and you can see why, right? I'm now pushing different values of different types into the interface, into the vector, sorry. And if I want to get back to using these specific identifiers here or format specifiers in print, I'm back to a type assertion to know what data came out in order to know how to process it. And if I start adding floats, well, I don't have a case for that, right? And so this is where the usability starts to kind of crumble because we're not really sure what kind of data is going to be in any given index position as we range over that vector. So I think, again, there's value in this case where we can define this vector still bound to a concrete type to be determined at compile time. And then we know exactly what the data is going to be as we range over it. So you can see here, however, that we're using that syntax I showed before to explicitly pass what T is going to be. And we have to do that in this case because it's not possible for the compiler to infer the type. There's nothing that the compiler can hang its hat on, so to speak. And so you're seeing here a case with this generic type where we're telling the compiler at the construction site what T is going to be. And then that's going to flow into the method set. And we're back to being able to work with one type of data and do that. And we can build and run this code. We can validate that it works, no problem. There it is. We can see the interlacing that happens here at the empty interface. And once again, the whole point here is that, we can change this out to a float 64. Maybe I can call this a float. I can now construct a vector of any concrete type, here being explicit. Then we can actually work with those floating point numbers, no problem. And we could go back to using a specific identifier like %f for our float. And there we are again. It's working. We didn't have to write another vector type. We didn't have to get into the complexity of the empty interface and reflection. So we're seeing here how we're able to leverage generics in defining a generic type. In this case, the underlying type being a generic type, a slice of some type T to be determined at compile time. Now, how does this work with our struct types? And how does this work when we start thinking about pointer semantics? Because everything I've shown you so far is really more around those value semantics. All right. Now, the code I'm going to share with you also is kind of showing another area where this version of generics that is being proposed could help solve some problems, right? And that's with these, these container types, right? Like these algorithm data structures, like in this case, a linked list, where the majority of that code implementing a linked list is the same. The only difference would be the data that's being stored in any given node. So I'm going to show you the beginnings of a linked list and then also show you some pointer semantic aspects of this which are interesting. But if we get back to it again, right? The point here I'm trying to make is I want to define a type named node that can store a data value of some type T again. And every time we're going to have some type T that has to be defined at compile time, we're going to have these square brackets put back in. Again, telling the compiler that T is the type to be determined at compile time. Don't expect me to be explicitly defining this anywhere in any source code file. So now that the node is a generic type, we're always going to be, writing that with that bracket T syntax again. It's not just a node, it's a node of some type T, a node of some type T. All right, so we've got our node storing some value of type T. And then again, we have this list, which is providing the first and last pointers to the beginning and the end of the list of some type T. So you can see here, we're going to turn list into this generic type of some type T, and we need that to apply it to our node. And we're using our pointer semantics for the linked list because those are the mechanics that we should be using. Now, I went ahead and I implemented an add method. And once again, you can see here that the receiver isn't just list, it's a list of some type T, a node of some type T. But here I wanted to use my pointer semantics. So in every one of these cases, we're going to be sharing that list of some type T. We're going to construct, look, here's a construction call. We're not being explicit with the type information here like you saw in main. We're going to carry over whatever value here is passed, whatever method we're binding for this list of some type T. That's the same T that we're going to use for the node construction. So we see we're constructing a node, we're wiring it into the linked list, and then we return that node using our pointer semantics. So it goes back again to this idea of that some type T. Now, how does all this work? Well, there's my user type. I'm going to define a type name user that we'll store in our linked list. And you can see on line 53, when I construct my list, I'm explicitly again telling the compiler that T represents type user. And since in this particular case, we're saying that T represents a user value, then our add methods, well, they get applied to that same value semantic or user values. And so we're storing values of type user in our list there. And we can validate that by displaying those values in print. But, we could also say to the linked list in this case, no, we want T to represent a pointer of type user. And we're going to use our pointer semantics here. And you can see here now on the add call, you're seeing me, when I'm constructing these user values, take their addresses. And you'll see here that these are addresses coming back out. So if we go into 3 and run it, you can see here that the data is being stored as values. The data is being stored as addresses based on how we're defining T. Now, this is really nice because I'm letting the user to determine what data semantics they want to work with for their list. They can work with value or pointer semantics. However, if you wanted to, in the implementation, we could do something like this. We would not apply pointer semantics here. Remember, this is just a list of type identifiers. It's just a list of names that represent types to be determined at compile time. But if I do this here and here, then what I'm saying in the implementation is that whatever type T is, we're going to apply our pointer semantics for data storage and our pointer semantics for adding a value to the list. Now, what that means is if I try to build this code now, we're going to get some compiler messages that I've got these mismatches now with our values and our pointers. So ideally, because I'm kind of restricting the list now into our pointer semantics, what's going to happen is we're still going to say that T represents a user type. We've already applied our pointer semantics in the implementation, both in what data is and the method. And so now what we do is we do those pointer constructions like this. Everything works. But we're kind of really locking the user into just using those pointer semantics and not giving them the ability to choose one semantic over the other. So it's something you might want to consider, especially with these types of data structures. Do we want to leave T open and let the caller, the user, determine whether T will be a value or pointer type? Or do we want to lock in those semantics, which could make working with this generic type a little less intuitive, but it might be something important for you to want to do. Okay, so I've now shown you a generic function. I've shown you two name types, two user-defined types, one based on an underlying type, one based on structs, and I've given you some kind of view of the world as it relates to pointers in this. Okay. We've got 20 minutes left, which is good, because there's a couple more things that are really important that I need to share with you before I'm done. And one of them is this idea of constraint. So far, with all the code I've written, there's been no need or nothing that would really prevent T from being a value or a type or any type. We haven't defined any or written code that requires constraint. And there's going to be times where there's constraints in what T can actually represent. So, oops, wrong one. So let me kind of share that with you. So if you look at line 13 and line 22, defining these user-defined types again, using our struct, and sorry, let me just get a drink. And in these two cases here, I'm adding a method named string, which basically stringifies what a user or a customer is. I hand-coded this, and I've made it look like JSON, but the idea is that I'm going to stringify a user or a customer, maybe for logging, who knows. So there we are. Now, since a user and or a customer can be stringified, and I may have a collection of each, I go ahead and I write a function called stringify. Now, if you look at the two stringify functions that I've provided, they each take a slice of their corresponding type, user or customer. They return a slice of string. And again, in 5 lines of code, I can construct the return slice. I can use our traditional for range loop to do that linear traversal, and then append the stringified versions of user and customer together. But the key to all of it is the method string, because that's where we're getting the intelligence on how to stringify a user or a customer. But again, these 5 lines of code, I think most Go developers at almost every level could quickly comprehend and have a general sense of what's happening. Okay, so we go back through our progression again, right? Can I have a single stringify function? We could again, Bill, we could use the empty interface again. We could do type assertions again, Bill. We could have a different case for each. It's not generic, but it is a consolidation of our other functions. Okay, But can we use the reflect package today to write a true generic version of stringify? And the answer is we can. Now, remember, we went from 5 lines of code again to about something like 12 or 13 lines of code, right? The complexity of writing the stringify function is much greater than we saw with that other print function. I mean, look at what I have to do. I mean, we saw this already. I got to validate that we even have a slice. I can construct a return slice of the right length. I can't use my for range, but I can iterate over I. But the big thing here is this, right? I have to be able to call the string method. And the reflect package is pretty cool. I can iterate over every element, find the string method for that, assuming that it's there. If it's not, I have to return something again. So the semantics change a little bit. But if the string method is there, I can call it, which I have to, and then take that stringified version of that data and append it to the slice. So here is reflect again, allowing me to write a generic function that can even call that method set of behavior. Now, look, it took me probably 15 minutes to write this code. That's with all the experience I have. And trust me, I had to look up the documentation. I didn't do this from the top of my head. So again, we're back to the idea that, you know, not every Go developer at every level could come in and look at this code and understand it and comprehend it quickly, as opposed to the 5 lines of code we needed when we weren't working with the empty interface or the reflect package. We were working with the concrete type directly. So what would this look like using our generics syntax? Well, hopefully, as you expect already, we're back to those same 5 lines of code. I'm trying to stress here over the last hour that one area here where the generics can really help us write code that is going to be more comprehensible is the idea that when we're working with these concrete types directly, we're able to leverage this goodness from the language, as opposed to when we start having to use the empty interface and we're now applying type assertions or the use of the reflect package, the complexity goes up. Here, the complexity can remain at the same level that we're working with any concrete type. So here we are again, right? Like, we want to work with a slice of some type T. And if some type T is a concrete type like this, we get to write code as if it was an int or a string or anything else. But again, because it's going to be of some type T, I have to do this. I have to apply my brackets again, let the compiler know what T is, and everything's good. But we do have another problem. You see, this function still requires the call to some behavior named string for every value of type T. And right now, we're not really giving the compiler that piece of constraint. There's a constraint here that T must be, a value of type T must exhibit the string behavior. Now, look, we write traditional polymorphic functions in Go all the time, right? And we do it with our interface, don't we? I mean, look, when you're writing a function in Go, you got 2 choices. You can ask for data. You can ask for data based on what it is. I can ask for a user. I can ask for a customer. Or you can ask for data based on what it can do. And we do that with the interface. In this case, what I'm saying is, I will accept a value of any type as long as that value exhibits the full method set of behavior defined by stringer. Stringer is applying a constraint to the data on behavior that we plan to execute, right? So the interface is already giving us the ability to define behavioral constraints on data that we want to pass into this function. And we really have the same sort of constraint situation here. We have to put a constraint on the type in this case, right? In this case, it's the data of some type. Here, we're going to say again that only types whose values can have this constraint on behavior string need to apply. So because we're using the interface already today in our traditional polymorphic functions, the idea of the spec is to use the interface again here to define the same sort of constraint. And func.stringer is already an interface defined for a method named string that returns a string. And so just like in your traditional polymorphic functions, when you're applying behavioral constraint, I will only accept data that can behave like this. We're going to do the same thing here, kind of flipping the table a little bit and saying, well, T can only be types where the data can exhibit this method set of behavior. So leveraging interfaces, once again, here in our generic functions to apply that behavioral constraint. And look, I've got my slice of user and my slice of customers. I can pass them to all these functions like I did before, right? This is getting boring. We saw this. I get it. There it is. Here's my stringified versions of this. I'm not going to add a new type here. We get that. But I will remove the constraint for a second so you can see the compiler message. And you can see how the compiler is saying to you, you're calling into this behavior named string on line 114, and I'm sorry, but this is undefined for T, so this isn't good, right? We need to apply that constraint. So we put the constraint back in, and now we're telling the compiler, yep, there's going to be a method named string here, and so make sure that T conforms to that stringer interface, and we're all good again. Okay, awesome. Okay, we've got 10 minutes, and that's good because I really wanted to have enough time to talk about number 5 here. And 5 is important because this is going to be an aspect of the draft that I think is still a work in progress. And it applies a constraint that we just don't have with our traditional polymorphic functions, because it's a constraint that's not necessarily on behavior, but really on the property of the data that we want to work with. So once again, I'm going to get rid of the new syntax. And what I want us to do is just focus on line 16 for a second. Now, on line 16, the idea is I want to write an add function that accepts a value of some type T and a second value of some type T, and adds them together to form a third value of type T that is to be returned. And the problem really is with the plus operator, because not all types work with the plus operator, right? Not all types work with plus. You can't add 2 user struct values together. You can't add 2 customer values together. We don't have operator overloading in Go. We don't have the ability to apply an operator plus method. So the problem here is I can turn around and say, okay, compiler, T is a type to be determined at compile time, but the use of the plus operator now also requires us to apply a constraint that it's got to be data that we can use in the plus operation. It's not tied to a method set, right? It's tied to the operator. So we currently don't have any mechanics for this in the language, right? Interfaces are being used for behavioral constraint. So in the current draft, the idea to handle this type of constraint is to use the interface again, since we're traditionally using interfaces to apply constraints. But since it's not method set bound, it's really type bound, to add this type list inside the interface to denote a list of types that now, in this case, the add function is constrained to. So we're constraining the add function now to be of these types. And when we say these types, that applies to underlying types. So Bill would conform to the constraint because Bill's underlying type is a string and string is in this list. So you wouldn't have to specify Bill in this case. Underlying types get matched as well. But what we're now saying is that we've got this special sort of constraint. Now, this is where things kind of break down a little bit. And the language team is rethinking some of this here, and they want your thoughts and ideas. Because when we do this to an interface, at least in the current implementation, right, I now have an interface that I can't use in writing a traditional polymorphic function, right? And this isn't very Go-like to define something that works in some cases and not others. So this is maybe a little bit of a hole in the current draft design that we need to explore a little bit more, because once I add a type list to an interface, that interface is only applicable to generics. It's no longer going to be usable in writing like a traditional. This wouldn't really make any sense, in a sense that I'm restricting this function to what it is, but then only this list of what it is, as opposed to not what it is, but what it can do. It breaks down. And the language team knows it, and the language team is starting to explore some different ideas here. But that being said, right now, this is what we have as relates to this type of constraint. Now, something else that is in the spec is the idea of the language defining some pre-declared type constraints. Just like we have pre-declared built-in functions, we could have some pre-declared type constraints. And one of them right now that's available is called comparable. And the idea here is you wouldn't have to define your own, say, interface with a set of types. These things can be pre-declared. And in this one, we're supporting what we're trying to do on line 29, because not all types are comparable, right? Now you might say, well, struct types are comparable, Bill. I can compare two Bill values together, yes, but you can't compare two slices together. So if T happened to be a slice of something, then this code wouldn't be able to run. So we have this idea too of pre-declaring. The other thing that is interesting, and I'm going to just move to it because of the amount of time we have, is that at least in the current draft, what is being experimented with is the ability to apply both a method set of behavior and a type list. Now, I'll be honest with you, I have struggled to find a very practical need for this. And part of this next year of getting everybody involved, looking, I want everybody to look at their current projects, whether they are at home or at work, and try to see where generics can add value, experiment with it, because there may be parts of the draft like this where we're supporting something like this, which adds some layer of complexity, but it's not really needed. And we won't know until we write enough code to validate that, yeah, we just didn't need this. And I can tell you right now, I haven't found a practical need for it. But I want to take this out for 1 second, because there's some interesting things here. Now, let me take this out again. What am I trying to do? I'm trying to write a function named match, which takes a slice of some type t and a value of that same type t. I'll be able to range over that slice, and for each individual value in the slice, call their match method, passing in find, returning an integer if it's found, or -1. So what do we know already? We know that t is going to be a generic type. We also know now that there's match behavior, so we need an interface that describes the behavior that we're calling here for the constraint, which is why I defined the matcher interface. But this is interesting, because the match behavior isn't going to be tied to a single type. It's bound to type T, right? And so when you look on line 70, I'm defining the matcher interface. The problem is that match needs to accept a value of some type T to be determined at compile time. And so now we have to apply our generic type list to matcher, because we need to apply that information to the method set of behavior. Okay, pretty wild. Now, as you saw before, right, I added a type list of person and food to matcher. Now, I absolutely don't need that constraint at all, because the behavior is here. And the only reason, again, I would need that type list would be if I'm trying to do other things with T, which again doesn't make any sort of sense here. I mean, I don't know. Like this is what find is already doing, right? I mean, find is doing that already, and there's no need for me to do anything like this. So it gets interesting when you start thinking about, maybe you don't ever really need to do this, which then could lead to the idea that maybe we don't have to put a type list inside an interface to apply this sort of property constraint. Maybe these type lists could live on their own in some other mechanic, since we're never going to need to combine the two of them. I don't know. I mean, somebody might come up with a need to have this. I just haven't found it yet. And maybe that's good that I haven't found it yet. And maybe it's good that nobody's found it yet, because it could solve this whole idea of it. We're breaking the interface by putting that list in. But this is something the language team definitely wants to hear your thoughts on. Okay, this is great. It's been an hour right now, and I got through at least the 5 examples that I wanted to. You'll notice that there are another, 5 examples here. 1, 2, 3, 6 examples here. And I encourage you to really look at these examples on your own. Example 6 is showing you how you can have multiple types in here. So you can define as many generic types as you need in the list. The other thing is that once you define a type with a constraint, then they all need to have a constraint. So you might see the use of the empty interface as a constraint in a multi-identifier type list, because that's how we satisfy that compiler now in constraints. So that's all that this example is trying to show. And line 7 is doing it's line 7. Example 7 is doing 2 things. It's showing you code where you're returning type T and how we handle 0 values. And it's also showing you some other interesting, I think, aspects of where generics could help to simplify some code. So that stuff's interesting. Then we've got swapping, slice constraints, some channel stuff, and some more complex type of data structures. Yeah. So hopefully, at least over that 1 hour that I've just provided, you have a good general sense on what the draft is sharing with you in terms of syntax, and some of the problems that we expect to be able to solve differently, and hopefully, I think with more readability and less complexity when generics comes in. And everybody's asking, when do you think that's going to happen? We're about to release version 115 here in August. We have 2 releases every year, August release and a February release. The earliest you could ever see this would probably be the August release next year. Though my guess is we're probably looking at the February release of 2022, my guess. But maybe if everybody really works hard together and we knock this syntax out, maybe in a year. All right, so that's what I've got. I'm completely open for questions now. I didn't see a lot of chatter there, but if you have a question, yeah, just take a turn. If you're comfortable unmuting, that's even better. Now, I know I didn't do that good of a job here, so somebody's got to have a question.
I've got a question, Bill. Not more about performance. I'm just curious. Have you been able to? One of the great things about Go, I think that a lot of people like, is fast compilation times. Do generics add any particular overhead over that? Have you been able to observe that on a bigger code base other than just the traditional hello world kind of examples that would significantly impact experience in that sense?
So here's a problem with the performance question, and I get it in every meetup. Generics has not been implemented yet. What you're looking at is a transpiler tool, so we can play with the syntax. So they do expect, depending on how heavy the code is using generics, for there to be a little bit of a compiler slowdown. I mean, this isn't free, but they are very focused in making sure that one of the trade-offs is not losing the compiler speed. So when I say it hasn't been implemented yet, I mean, again, all we have is the transpiler tool. So there's nothing to gauge in terms of performance. But just think of this. I like sharing this because it gives you an understanding of some of the engineering decisions they have to make, okay? When they finally decide it's time to actually implement this in the compiler, they have to make this engineering decision. Do we literally create an individual type and or function for every call to a new type, right? Or new construction? Now, if we do that, you're gonna have functions that are lean and mean and perform and even potentially reduce allocations in some cases. But what's the trade-off to that? Larger binaries, depending on how much of that code base is leveraging generic types and how many types you introduce. So there's a balance between, let's say, code performance, binary size, and how long does it take the compiler to produce all that code. So the opposite of that is, well, you could leverage the same kind of generics mechanics that we have today for the built-in functions. So instead of writing out 10 different functions for 10 different types, we could still implement a single function that does it all for all those types, right? Now, that function wouldn't run lean and mean as an individual one, and you probably now can't escape allocations at all, which we don't do anyway with our traditional polymorphic functions. But it would definitely help with the compiler because you're writing one function. You're not writing maybe 10 across the whole spectrum. So it's a almost impossible question to answer right now because I don't know if the teams even made decisions yet on what they want to do. I'm sure they're thinking about it, but that decision hasn't been made yet. And that's going to be fun when they make that final decision because you're going to see everybody split on, no, I don't care about binary size. I want my performance. And the other side's going to go, yeah, I want my compiler performance back, right? And it's going to get fun. We're just so early in the game right now. They don't want to focus on that because we're not finalized on the syntax yet, like I showed you with the type lists. So hopefully that answers your question.
Yes, thanks.
Did Jonathan want to ask his questions, or do you want to just read them out from chat?
Yeah, I can talk. Yeah, I was just wondering how the community, and I'm very new to Go community, but how are we thinking about the proposal's impact on the learning curve for Go?
Yeah, so I'm trying to figure out what direction I want to take this question in. One of the things that I've expressed to the Go team a couple of times is that before this is released in any version, they need to produce documentation in the form of guidelines, idioms, best practices, and a bunch of code examples. I've asked them to lay down the educational foundation for the do's and don'ts for generics. And not just because I'm professionally teaching Go week to week. It's because everybody's teaching Go. You're teaching Go when you're in that pairing session. You're teaching Go at work to that person next to you. And we all need this base foundation to make sure that we're using generics, at least this release, when it's reasonable and practical to do so. So what's going to happen, let's not lie, we see it with channels already. When somebody is new to Go, one of the very first things that happens to their code bases is they go concurrency crazy. Start using Go routines where you really don't need them. You start using channels where you really don't need them. But you want to work with these constructs. You kind of force them in. And it takes about a year for most individuals to sit back and go, I can't believe I did that. Now I've got to maintain that mess in production. It happens to a lot of, it happened to me. It's just like, it just happens. So I think we have that already in place, that understanding around channels of how everybody comes in and abuses them and then eventually rips them out. And so what I'm hoping is that we keep talking about that. So when this gets released, we all take a pause and we go back to this idea of, is it reasonable and practical to use a generic function here or a generic type over what we can do today, even with reflection, or just using the concrete type directly, right? It's, you know how many code bases I see that are already over abstracted and interface abuse, right? I mean, we see it. So is generics adding another layer where there's potential abuse? Yeah, of course. So we're gonna have to come in as a community and just have the conversation on those open source projects. And you're gonna have that conversation on your team, like any engineering conversation, if it's really reasonable and practical to do so. I don't think it makes the language more complex unless you start using it. And I don't think there's, outside of the empty interface and these sort of container types. That's really what this first release is going to be about. So yeah, it adds some complexity. So we have to minimize the usage, and we have to just make those smart engineering decisions. I wish there was a silver bullet here, but there isn't. I'm not afraid of it. I'm not worried at all. It just becomes a teaching moment that you're going to have to embrace.
Yeah, I think coming from a language that has generics, C sharp, I can kind of see some differences. Like, for example, the type constraints, there's no keyword that kind of highlights that. And you kind of talked about how there's different options about how you can make type constraints work. And I'm looking at how many keywords are in C sharp. There's 79, and Go has about 25, it looks like. So it's almost like maybe as these languages evolve, putting in some more keywords for new features in a constrained and controlled way could help, because it gives that clarity to, having type and then the T, and then after that, the type constraint. There's three things there which it's hard to kind of know how they relate.
No, I hear you. And the current draft also, with the square brackets, states that you don't even have to put the keyword type there. I'm doing it because I feel like there's more clarity using the keyword type inside the square brackets. But you could also, you don't need it even in this version of the transpiler. And that might end up going away. I mean, and the funny thing is, I haven't even really tried it, but I was told by Robert that, we'll validate it works on one, that they needed it with the parentheses. With the first version, they needed it with parentheses, but Robert told me that this would work. I'm experimenting now with you, so. And it did. So you don't need to put type here anymore. The brackets eliminated that. But I had told Robert I kind of liked seeing personally the keyword type there. It helped me. And maybe it's because I've been working with this for 2 months, so my brain is starting to be wired in a little bit on the syntax. And I told him I'm gonna keep teaching with the keyword type. But we might end up at the end of the day like this, and yeah, that might even be working better for you, because now there isn't 3, there's just those 2, right? But
Yeah, and
this is why.
the
Yeah, go
other
ahead.
thing I kind of noticed was the compiler warning errors or messages. That also is kind of like part of the user interface for a developer. So having those actually part of a spec in some way could actually help to say, like, what kind of examples of, hey, maybe you should use this to constrain the type so that you can use dot string or something.
Yeah, these are all these ideas you have. I really want you to write them down and share them, because the survey that I've given you a link to is from the Go team, and it's really for people who, like me, don't want to get on the mailing list, don't want to write an issue, don't want to get into public debate, just kind of want to share their thoughts. And you have an opportunity to do that with the Google survey, and they're reading all of that, I promise you. Plus, if you have really interesting ideas and you don't feel like getting it directly into the public debate, you can also send me an email and we could talk about it. And then that's stuff that I can send directly to the Go team as well, and getting their thoughts. And then they may turn around and say, yeah, why don't you put that up in an issue so we can, we can document it. But those are all good ideas. But the thing is, you got to play with it. You got to try to take code that you have and see where it works and see where it doesn't. But believe me, you're looking at 11 examples. I probably had 30, and these are the ones that where it started to make sense, and all the other stuff I was like, nope, 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 nope. Let's see, Mark, what are your thoughts about suggestion to use type foo t any struct where type any equals? I'm not sure I fully understand, Mark, other than the empty interface isn't really a constraint. So I'm not sure I understand, Mark. Maybe you can give me an example.
I can probably unmute if that works.
Yeah.
So there was a suggestion on the mailing list the other day where sometimes you need to have a constraint to constrain your T for your type or whatever that is. And so then the idea is the sort of analog we have with interfaces where we use the empty interface. But if you had to use, basically with the square brackets, you have to have something there to sort of differentiate it between using it as an index. So currently we could use type, but that's optional. If you had something after it, like the actual constraint, and you made that mandatory all the time, then you don't need type, and you just have this is the T, and this is the definition of an empty interface, or it's a stringer or whatever else you want to use. If you haven't seen it, then I guess you don't have any opinions on it.
Well, you don't need type, like I just showed you. You don't need type now with the square brackets anyway.
I think there's still one case where you require it because they can't differentiate it. At least that's what I last saw, because I've been playing with the latest.
Yeah, I'm on vacation, so I haven't looked at the mailing list in a bit.
That's good.
There may be. I like type there anyway. Maybe, I don't know. I haven't run into that problem yet, so that one's hard for me.
Yeah, I don't have thoughts on it. I just thought it was interesting because then you have the similar analog to with interfaces where you have, this is the name of my argument, or what I'm going to call the variable or the type, and then this is what fits in that space, like an interface or otherwise. So there's sort of, it mirrors what we have with interfaces and types, even though I understand they are technically a little different.
I would just tell you that the idea of having to find another type to do that, I'm trying to reduce the number of types.
You don't need to, I guess, is the thing. You could just use the empty interface.
You just use the empty interface, and then that would be more explicit. Yeah. Okay. Yeah. All right. Does anybody else have any other questions here? Okay, cool.
I think you're the one that's up really late, but everyone seems a bit tired.
Yeah. I'm adding my email to the chat. So once again, I hope you fill out the Google survey. Don't feel like you got to fill it out now. If you're gonna spend some time experimenting with code and working with this, do that first, and then you can give them some feedback. If you come up with any interesting examples that aren't currently represented in the training material, I'd love to see it. I'm trying to collect as much as I can practical examples that everybody can learn from. So if you come up with something interesting, please share that with me. Maybe we can put it back into the repo. And then eventually it could be part of a larger education kind of setting, whether it's a talk or things like that.
So
and then again,
you said you've been running training and stuff. Where have you been doing training with this, or is it just in meetups and things?
No, I'm not teaching generics other than these meetups right now, but eventually it's going to happen, right? And then for anybody who wants to teach the generic syntax like I'm doing even over the next year, these are examples that you can leverage, right? All that's open source. So I'm trying already to put together small practical examples. And if you see there's an emissions folder kind of showing you some examples of things that we're currently not going to be able to do, at least with this draft. I don't even think I want to teach this formally in a syntax class. I think I'd rather somebody come to me and say, Bill, we've run into this problem. And then I can say, okay, I think this is where generics comes in. and then maybe teach it that way. But as you already saw, we in 1 hour I was only able to get through about 4 or 5 examples. It also eats up a lot of time.
But it was really good to hear the motivations and thought processes and the different ways you could potentially solve it. I think that's really important too.
Yeah. Yeah, it helps me understand where we're going with it, right? All right.
So no more questions? Adam said he had some questions, but he's already popped off, so I'm not sure what's happening there. So he's probably got a tight deadline, time limit.
Okay, that's fair.
Can I just ask one more?
Yeah.
Given that no one else has got any, is it possible to compile a module with generic types and then use that in another module? I'm just trying to work out how the compilation's working.
I haven't tried to do that with the transpiler, so that's interesting. Actually, I don't know. I don't know at all, John. That's Jonathan, right?
Yeah, I know with C# and .NET, you can create a generic type in an assembly and it gets compiled into intermediate language, and then you can use that in another module, another
You'll be
assembly.
able to do that. When this is implemented, you'll be able to do that for sure.
Yep.
That's you'll be able to write third-party packages that are using generic types, and that's not an issue. I just don't know if the transpiler is working across packages right now. That I don't know. I haven't done anything that large. At some point, if you listen to the podcast, Robert and Ian were on that last week, and I think it was Ian made a comment like, at some point it just won't make any more sense to fix bugs and to do anything more in the transpiler. At some point we're going to have to put a real implementation in, right? And I thought that was interesting, because the transpiler does have bugs. I run into them here and there, but right, I mean, how much more engineering effort do you put in that as opposed to getting a final implementation in the compiler? But for sure, we'll have that functionality without an issue.
Right.
Thanks very much for your questions, Jonathan. That's really good. And I just saw Kevin's put a link to the podcast in the chat as well. So thanks very much, Kevin.
Thanks, Kevin.
Alrighty. So yeah, not as chatty as it could be, but as you said, it's early days, and it would be really good to play around with the code too, to kind of go through stuff in your head. And it's interesting too, because a lot of people probably got different perspectives of generics, like they've used it in different languages. You don't want to map too much of that onto it. It's kind of interesting.
Yeah, I think the baggage, especially from the Java communities, is super interesting. I meet more people from the Java community that have switched to Go who are really nervous and worried about generics, I think more than other languages in general. I don't have the empirical data to back this up. I'm just from what I'm experiencing, I find it really interesting. I didn't code in Java. I didn't really like the language, but it seems like there's this fear being carried over, especially from that original community, that this is going to do all sorts of damage to programs in the language. And I go back to, we just have to be disciplined and learn from those past mistakes, and we should be okay.
Yeah, I think it was a good example of using Go routines. It's a really good example of potentially overusing generics when you don't need to. Alrighty. Okay, well, look, thanks very much for your time. I can't imagine staying up this late. I really appreciate you doing that. Are you teaching tomorrow morning?
No, I got another meetup in a couple of days, but I'm good tomorrow. I'm on vacation, so I get to sleep in.
Cool. Are you on vacation away from your home, or?
Yeah, I live in Miami, Florida, but I'm out in San Diego this week.
Miami sounds like a holiday destination.
Yeah, well, I actually worked out because I was here at 1 in the morning instead of starting at like 4, right?
Okay, yeah, it has
So
worked out a bit.
it worked out.
Maybe looking at generics at 1 in the morning is a good test of if it's a good implementation.
Are you got any training coming up? Are you doing online training? Phil?
Yeah, maybe. Yeah, I got some. I think at the end of August, I have a service class. I'm going to try to do some dgraph. I've been playing with dgraph this year. So I got a class around dgraph and services in Go. I got my service class. And then the corporate training kind of kicks back in September.
So it's
August is a slow month.
yeah.
Yeah.
Yeah, I remember
Yeah.
you were at Sydney GopherCon, so I was there as well. So I remember that. Yeah. So
Yeah, and I think GopherCon is gonna. I think GopherCon is going to be virtual. We know it's going to be 100% virtual this year. So planning on doing a workshop there as well.
yeah, I haven't heard about the Sydney GopherCon organisers. So do you mean the US GopherCon? Is that
Yeah, the US GopherCon. They really did want to have a physical event, but Disney, I think, eventually just said no, we're not doing it.
Mm.
So all that shut down. They tried really hard.
I think Chewy has confirmed that GopherCon in Sydney is probably not going to be happening this year.
Yeah,
unfortunately, as well.
he seemed. Oh, he just lost his job recently, didn't he? So he's probably
That too,
got some different.
right at the start of the lockdown.
Yeah. Yeah, so bad timing. So yeah, I was thinking he seems a bit distracted too. Actually, Louis was to be on tonight from Adelaide. Do you remember we met Louis, Kevin, at GopherCon? Yeah, because I know he's recruiting, so
Probably stuck launching a satellite.
yeah, pretty exciting. They're using Go on a satellite project, so they've got to really be rigorous about their code because they can't really do updates once it's launched. So it's really interesting space to work to work in. But yes. All right. Well, look, I might just end it up there. Thanks very much, Bill. This has been really good. And yeah, it's really great to get into that. And I think your examples are a really good place to start for people getting into it.
Awesome. All right. So I hope maybe I'll be invited back in a few months if anything major changes or if you have other things you want to see. And other than that, keep meeting. I love meetups. And this to me is this is the best medium we got right now, these meetups. So
yeah, you mean just because we don't have conferences and things, this is like mini conferences. Yeah,
for sure. So keep doing this every month. I like meetups better than conferences anyway, honestly.
Yeah, it's a bit hard to have that informal chat though. It's a bit awkward, but yeah.
All right. So good evening, everyone. Hopefully, don't be strangers. Reach out if you need anything. I'm around, and hope to see everybody again soon.
Thanks very much, Bill.
Thanks a lot.
All right.